In the previous lesson, we learned how to solve polynomial equations by graphing, right? We would graph the polynomial equation. You would find the x-intercepts. You would get those answers. You would synthetically substitute to depress your polynomial to a quadratic, so you could solve that quadratic, maybe with the quadratic formula or maybe by factoring. Anyway, that was the previous lesson. Today, I want to use the same worksheets and talk about just factoring polynomials by graphing. So let's jump right in. These notes, we are going to continue them. We still need to cover complex conjugate theorem, but before we do that, let's take a look at the worksheet. 5.6 was all about factoring. Well, the first half was plug in a number and find your answer, right? Plugging in -3 and plugging in 4, but this bottom half, that's where we actually had to find the other factors given one factor. So example 19, they give you this factor right here. Okay, x minus 3 is a factor, and they want you to find the other factors. I want to show you that you could actually graph any of these polynomial functions, and the graph tells you a lot, right? Let's graph it. So here's the graph. Notice that it only has one x-intercept, one solution, yay? And I think right now is a good time to talk about how to interpret graphs. So if we see that a graph, let's say, crosses right through a certain value, then that would be a singular answer, right? Like that would be x equals -2 in this case. But let's say your graph only touches at a certain point and then it comes back up, then this answer of 1 has a duplicity of 2, right? And technically it could have a duplicity of 4 or 6, but the bottom line is the duplicity is even, okay? Again, if it crosses through, that's just a singular answer. So if it crosses at -2, then it's a singular answer at -2. If it just touches, then that answer, x equals 1, might have a duplicity of 2. Right? It could be x equals 1 2 times. If it crosses through a point, but there's like this little squiggle, like this like snake-like curve, doesn't this remind you of a cubic function? So this must mean that the answer, x equals 3, could have a duplicity of 3. That means that the answer repeats 3 times. Do you guys kind of understand that? Once again, if you see that it crosses through, that's a singular answer, x equals -2 in this case. If it touches, that's x equals 1, but it could have a duplicity of 2 or 4 or 6, an even duplicity. So in this case, it might have that x equals 1 2 times. But if it crosses, and right as it crosses, it does that little like squiggle that a cubic function does, then it might be an odd duplicity. So it could be x equals 3 3 times. Make sense? Kind of, sort of? Okay, well anyway, obviously these guys aren't part of the graph. So what do we have here? We have that answer, yeah? And I'm telling you right now, this will have an odd duplicity. So it's obviously not 1 because it didn't cross right through it. It crossed in a squiggle, so it might have a duplicity of 3. So when I look at the degree of this polynomial, the degree is 3. How many answers am I looking for? 3. If the degree is 3, if the highest exponent's 3, then I'm looking for 3 answers. Now you might be thinking, well, maybe the answer's 3 and the other 2 are imaginary. That would be true if it actually crossed in a single line, because then that would be a single answer of 3 and your other 2 would be imaginary. But because I see this squiggle as it crosses through at 3, I know that reminds me of a cubic function, so I know that this answer has a duplicity of 3. Okay? Now, let me verify that with you. Let's just go back to the original question. This polynomial, this is one of its factors. They tell you that in the instructions. It says, find the other factors of this guy when you know this given factor. So what do? We take that factor and we put the +3 in the box. We're going to do synthetic division because we know that when we divide anything by one of its factors, your remainder should be 0. Okay, so I'm going to divide this cubic polynomial by x minus 3 using synthetic division. My list of coefficients, there's a 1 on the x to the third, a negative 9 on the x squared, a 27 on the x, and a negative 27 as a constant. So as I go down, I combine. 1 plus nothing is 1. As I go up, I multiply. 3 times 1 is 3. As I go down, I combine. Negative 9 plus 3 is negative 6. As I go up, I multiply. 3 times negative 6 is negative 18. As I go down, I combine. 27 and 18 is 9. As I go up, I multiply. 3 times 9 is 27. And of course, my remainder is 0 because I'm dividing by a factor. They told us it's a factor. If you do not get 0, then you got to check your work and find your mistake and fix it. Because the whole purpose of us plugging in this factor, or not this, yeah, but this factor, this value of 3 is to get a depressed polynomial. You see, x to the third, that's kind of hard to work with. Actually, it's not. We could have actually taken, I think, no, we couldn't even factor by grouping. So we're plugging in the 3 to get a depressed polynomial to get it to be a quadratic because we're really comfortable with quadratics. And right here, we do have a quadratic in blue. What do we have? We have 1x squared minus 6x plus 9. And they want us to find the other factors. So we're using this depressed polynomial to factor it. It is a quadratic trinomial where the a value is 1, your b value is negative 6, and your c value is 9. It's really simple. Just think what times what is 9 that if you combine together is negative 6. What times what is the c value that if you combine together is the b value? That'd be negative 3 and negative 3. So given this factor, the other factors are these guys. So if I wanted to write the original in completely factored form, all I have to do is take this one up here and bring it down here to the front. Believe it or not, this is all 3 binomials multiplied together. If I did distribute x times x, and then distribute, and then combine like terms, and then distribute to all 3. So if I distribute everything and combine everything, this it would take me back to this. This is the factored form of this. Make sense? And of course, if I were to solve this equation, like if I had it equal to 0, and I would solve it, I'd have to split each of them equal to 0, which would show you get the answer x equals 3 with the duplicity of 3. There's 3 of them there. Make sense? So that's going back to the graph itself. We saw, or we should start learning this right here. It crosses through 3, so the answer is 3, x equals 3. But if it crosses in a straight line, then it's going to be a singular answer, x equals 3. If it touches at 3, then it goes back up. Then it has the answer x equals 3, but it has a duplicity of 2. But if it crosses kind of like a cubic function, it crosses right through the 3, but it has this curve like a cubic function, then it has a duplicity of 3. That's where we get this answer, x equals 3. It happens 3 times. It has a duplicity of 3. In factored form, that makes total sense. The x minus 3 is happening 3 times. Let's jump to number 27. We have a 5th degree polynomial, and they give you one of its factors. One of its factors is x plus 1. Now, they want us to find the other factors. We're going to go to Desmos. We're going to type this in. It would be nice if we would actually see that it crosses the x-axis 5 times at different locations. That would be the easiest situation for us because we'd be done. All we'd have to do is come up with the binomials of where those answers came from. But when we graph it, we see how many x-intercepts? 4. How many answers do I want? 5. So I see 4, but the negative 1 has a duplicity of 2, right? And yes, it could be of 4 or 6, but here's the deal. You know you want 5 answers, and you know you have 1 right here, and it's only 1 because it's a line that it goes right through. That's 1. This is actually 2. So 1, 2, 3, 4, 5. Okay? So we have the answers. Let me write it over here. We have the answers x equals negative 2, x equals negative 1, and this one right here, we're going to just underline it in blue because that has a duplicity of 2. Then we have x equals positive 1 and x equals positive 2. Okay? So if we know those are the answers based off of this graph, and of course this one, this x equals 1 has a duplicity of 2 because it's like a parabola, okay? So I want to find the other factors. I could use these answers and just think, where did these answers come from? They came from binomials that were set equal to 0. So this first answer, this x equals negative 2, it came from a binomial set equal to 0. And you could actually show the work to set it equal to 0, add 2, and it came from x plus 2 equals 0. And you could put that binomial in parentheses. Does that make sense? Yay? Nay? Okay. Now that second one, where did this answer come from? X equals negative 1. It came from a binomial set equal to 0. What is a binomial? X plus 1 equals 0. Isn't that right? Okay. And you know what? It has a duplicity of 2. We saw it on the graph that it had a duplicity of 2. What does that mean? That you're going to have to write it again. X plus 1 equals 0. Okay. Now, this other one over here, this x equals 1, where did that one come from? X minus 1 equals 0. And this last one, the x equals 2, where did that come from? That's not confusing, right? It's pretty simple and straightforward. You get your graph, you look at where it crosses, write your answers. Where did those answers come from? They came from binomials. If you see that it has a duplicity of 2, write it twice. X plus 1 equals 0, x plus 1 equals 0. So I'm going backwards in the sense that what part of your solving this polynomial or factoring this polynomial, what part gets you here? That's when you apply the zero product property, where you split all of your multiplication up and set them each equal to 0. So we're going to work backwards and we're going to put them all together again. Instead of splitting them apart, we're going to put them all together again. So we're going to have the binomial x plus 2. We're going to have the binomial x plus 1. Again, x plus 1 has a duplicity of 2 times x minus 1 times x minus 2. Believe it or not, guys, this fifth degree polynomial, the completely factored form is this. Okay? Of course, like if you wanted to completely work backwards, you would distribute, combine like terms, distribute, combine like terms. That will get you back to the original. But this is your factored form. So I just wanted to show how you could use Desmos to get your answers. You write your answers. I like writing the answers at the bottom and then showing my work backwards to get to here. Does that make sense? So they gave you a factor. They want the other factors. What are the other factors? It's another x plus 1. If they already gave you an x plus 1, it's another x plus 1, x plus 2, x minus 1, and x minus 2. Any questions? No? So let's go back to our notes right here. Complex conjugate theorem. A theorem is a truth in math, okay? And do we remember conjugates? What is a conjugate? What is a conjugate of x plus 5? X minus 5. You guys remember that from semester 1? Whatever binomial you have, the second term, the sign changes, that's it. Not the whole thing, just the second term. Now, we're talking about complex numbers, and what are complex numbers? It has a real part and an imaginary part. So it says if a plus bi is a solution, then so is the complex conjugate, a minus bi. So for example, if I tell you 3 plus 2i is a solution of your polynomial function, then 3 minus 2i must also be a solution of your polynomial function. Yeah? If I tell you 7 minus 1i is a solution, then 7 plus 1i must also be a solution. The conjugate must also be a solution. Okay? So, for example, right here, they give us 2 zeros. They give us 2 answers. We have the answer, and you might as well write this down. We have the answer x equals negative 5. And we also have the answer 3i. But the theorem about complex conjugates say if an imaginary is an answer, this positive 3i, it is an answer, so that must mean that it also has negative 3i as an answer. Yay? Now, of course, like if I would have said, oh, one answer is 5 take away 7i, then the other answer would be 5 plus 7i. But it's even easier than that. They just give you 3i. Okay? So if they give you 3i, there is no number in the front of 3i. You could imagine a 0 plus 3i. What's the complex conjugate of 0 plus 3i? 0 minus 3i. So 3i is an answer. That must mean that negative 3i is an answer. Anytime you have an imaginary value as an answer, the opposite must also be that answer, right? Or the complex conjugate must be that answer. That comes from, if you really think about it, where do imaginary values come from? Where does 3i come from? From taking the square root of a negative, right? Okay? So whenever you apply a square root in an equation, you have to put a plus or minus in front of your answer. So even on the quadratic formula, you have a plus or minus in front of your square root. So if you ever have an imaginary value or a complex number, the complex conjugate must also be your answer. So when I tell you that your answer is negative 5 and 3i, and I want you to tell me the polynomial function that gives you those answers, what degree must it be? What degree must my polynomial function be that gave me these two answers? 3. Why? Because if I'm telling you this is an answer, that's like giving you two answers, right? So you have a total of 3, one real, two imaginary. Here's my one real answer. Let me write my two imaginary answers. X equals 3i and x equals negative 3i. So we have those three answers. I write them on the bottom because I'm going to work backwards. What do I mean by working backwards? The answer x equals negative 5, where did that come from? Came from the binomial x plus 5 equaling 0, right? And you could actually show your work. You go plus 5 plus 5. Where did the answer x equals 3i come from? It came from a binomial. What is that binomial? Pretty simple, same process. Just move it over. And it came from x minus 3i set equal to 0. Isn't that right? Same thing with the other one. Plus 3i, plus 3i. Where did it come from? It came from x plus 3i set equal to 0. Are you with me? Yay? So now, if zero product property allowed us to separate them and set them each equal to 0, we're going to work backwards and put them back together and set them together equal to 0. So I'm going to put them together. The x plus 5, the x minus 3i, the x plus 3i, and it is now equal to 0. See, I'm working this whole problem but backwards. Now, I need to do a bunch of distribution and a bunch of combining like terms to get to my original polynomial equation that must be at least degree 3, right? To give me these three answers. So where should I start distributing? Should I start right here? X times negative 3i. I highly recommend to start by multiplying the conjugates together, because I hope you remember from semester 1, when you multiply those conjugates, the imaginary values disappear. It ends up being nice and beautiful. Check it out. What is x times x? It's x squared. What's x times 3i? It's positive 3i with an x. What's negative 3i with an x? That's negative 3i with an x. What is negative 3i times positive 3i? Negative 3 times positive 3 is negative 9. But then you got I times I, which is I squared. And I wrote it in red because whenever you hear I squared, you need to think what? Negative 1. I squareds really are negative 1. So what happens with these middle terms, the negative 3ix and the positive 3ix, those are complete opposite values. Those disappear. And how about a negative 9 times what we have is a negative 1. What's a negative 9 times negative 1? Positive 9. So what I have here is x squared plus 9. Isn't that right? So I really have x squared plus 9. That is a binomial. But I still have this other x plus 5 that I need to multiply by. So I'm going to just rewrite it up here. X plus 5. And I guess I could have put this on this side. It doesn't matter what side it's on. You're going to have to distribute again. So let's distribute. Let's go with x squared times x. That's x to the third. X squared times 5. that's positive 5x squared. Distribute positive 9 times x, that's positive 9x. Positive 9 times 5, that's positive 45. And there is nothing to combine. Ladies and gentlemen, this is your cubic polynomial function or equation, if you put that equal to 0, that will give you the three answers, negative 5, 3i, and negative 3i. So this is the final skill that we're acquiring here on chapter 5, where I give you answers, and I'm going to give you an imaginary answer. And remember, when you see that imaginary answer, the conjugate is also another answer. You just don't see it. I'm actually giving you two answers in one. Okay? Any questions on that? If I were to graph this third degree polynomial function, I would see that it crosses the x-axis only at negative 5 as a line, not as a squiggle, because it has no multiplicity. It just crosses right through negative 5. And the other two answers are imaginary, which means that if I were actually solving with factoring, I'd have to use a quadratic formula, or I would eventually apply a square root, which would give you a plus minus 3i as an answer if you were solving. Anyway, let's take a look at another one. This last one down here, I give you that. We have those three answers, and I want the polynomial equation that gives us these answers. Let me ask you this right from the start. What degree do I need on this equation? Fourth degree equation, right? It has to be a fourth degree polynomial. So let's start working this backwards. I'm going to start with my imaginary first. I'm going to put x equals 3i, and also x equals what? If x equals 3i is an answer, what's another answer? Minus 3i. Okay. Then you got your other answers, your x equals negative 2 and your x equals 1. Okay, those are your four answers. We need to work backwards to get to the actual polynomial function. And of course, I would always start with our imaginaries. Let's move them over. So the answer x equals 3i came from the binomial x minus 3i in parentheses equals 0. The other one came from x plus 3i equals 0. Is this making sense? And the other two answers came from what? X what? Plus 2 equals 0. And the last one? X minus 1 equals 0. So we're going to take all these four different binomials and put them together. And of course, we need to start distributing. So always start with your binomial and the complex conjugate, right? So let's begin right here with these guys. Let's distribute x times x is x squared. X times 3i is positive 3i with an x, negative 3i with an x. And then we have negative 3i with positive 3i. That's going to be a negative 9 with an I squared. So what do I actually get as an answer when I multiply the complex conjugate with the complex number? X squared plus 9. X squared plus 9. Why plus 9? Because I squared is really a negative 1. So I really have a negative 9 times negative 1. That'll give you the positive 9. Make sense? So right here, I'm going to keep these in parentheses. The x squared plus 9, I want to keep them in parentheses. I still need to multiply this x squared plus 9 by this x plus 2 and then by this x minus 1. Okay? And it doesn't matter which order you multiply in. We could multiply these two together, get a quadratic trinomial, and then distribute, or we could multiply this one with that one, or this one with that one, but the bottom line is we have to multiply all three of them. I am going to distribute this binomial times that binomial. Okay? So when I go x times x, we'll get x squared. X times negative 1 is negative 1x. 2 times x is positive 2x. 2 times negative 1 is negative 2. When we combine the middle terms, we'll get a positive x in the middle. So you really have x squared plus 1x minus 2, and that is the trinomial that we get out of multiplying both of those binomials. So what we must do now, we already multiplied these two together and got that. We multiplied these two together and got that. We need to multiply now both of these together. We need to multiply both of these together, okay? And maybe instead of working up, maybe you could just rewrite it up here, the x squared plus 9 multiplied by x squared plus 1x minus 2, and distribute. X squared times x squared is x to the fourth. X squared times 1 is 1x to the third. X squared times negative 2 is negative 2x squared. And then distribute the 9 times x squared, that's plus 9x squared. 9 times 1, that's plus 9 with the x. And 9 times negative 2 is negative 18. Combine like terms. You could combine the negative 2x squared with the positive 9x squared, and now you'll have your final quartic polynomial equation, x to the fourth plus 1x to the third plus 7x squared plus 9x minus 18. If you put equals 0, that would be the equation that gives you those answers that we started with. That's a lot of work, fun stuff. And that's the last skill that we're covering in class today. We do have homework. The second worksheet, 5.7, the last two questions, I give you answers like this, and you have to work backwards to get to the original polynomial function that gives you those answers. And of course, one of those answers will be imaginary, which means I actually give you two answers, right? If you see a negative 2i right here, then your answer will be a positive 2i. If you happen to see like a 3 plus I, then the other answer would be a 3 minus I. So complex conjugate, if I give you one answer, the complex conjugate will be the other answer. Write your answers at the bottom, work backwards, distribute, combine like terms, and you will eventually get to the original polynomial that gives you those answers. If you were to graph this guy, you would see that it crosses at two locations, at negative 2 and at positive 1, and the other two answers are imaginary, giving you a total of 4 answers on this fourth degree equation.